Okay, so thank you very much to be with us on this Sci Cafe talk on the 13th of November. It's a great pleasure to have as a speaker one of the most cited scientists that we have here in Hellenic Mediterranean University. It's Professor Michael Tatarakis. He's professor in the Department of Electronic Engineering. He holds a PhD since 1997 from Imperial College in London. He's also over there an honorary visiting professor, and nowadays he's a director of the Institute of Plasma Physics and Lasers. The scientific work of Professor Tatarakis can be located in the area of applied physics, and more particularly in plasma physics and lasers. More things, I think, that Professor Tatarakis Michalis will tell to us. His work has received more than 5,500 citations, and his H index is 40. His publications include publications in all the Nature family journals, Nature, Nature Physics, Nature Communication, and more important for the physicists, a lot of publications in PRL, which is among the physicists, if you would like to be called as a successful physicist, you should have PRL, not Nature, nothing else. Just PRL is enough. So, Michalis, thank you very much for your contribution. The floor is yours. You can share your screen, and your presentation starts right now. You have around 45 minutes for your talk, and then we will have the Q&A session. Thank you very much, Michalis.
Kostas, thank you very much indeed. Let me start my share screening. So, Kostas, thank you very much for the introduction. I'm very happy to be here with you for this Science Cafe initiative. And thank you very much for your effort to initiate this Science Cafe action. So for the participants that are not from the Hellenic Mediterranean University, I would like to welcome them to Hellenic Mediterranean University and the Hellenic Mediterranean University Research Center and the Institute of Plasma Physics and Lasers. I would like to introduce you to the topic. Today I will talk to you about a first demonstration of current-induced electrothermomechanical instability anisotropic growth in metallic wire targets. So let me introduce you to the field. When we have a current which flows through a wire, there is a heating of the wire, and the wire changes phase from solid to plastic, gas, and plasma. So there are various phases that the solid goes through when it is under a current flow. For this work, I would like to thank my colleagues that you can see here, but also all the other colleagues they are members of the Institute of Plasma Physics and Lasers. The best way to introduce you to the field is to do a small introduction about the research center. The research that I will present you today is a follow-up of the research which was published about 2 years ago in Nature Communications, entitled The Influence of the Solid to Plasma Phase Transition on the Generation of Plasma Instabilities, also in Plasma Physics and Controlled Fusion. And a follow-up of these two publications are in preparation for PRL. Now, as I said earlier, the best way to introduce you to the field is to say a few words about the Institute of Plasma Physics and Lasers. It is a research institute of the Hellenic Mediterranean University. After evaluation from the NCRT, IPPL is one of the 2 access points of the National Research Infrastructure HELASI-H. It is a center of excellence in research and education, not because I'm telling this, but because we have been evaluated by the Marie Curie Excellence Grants. It's a coordinator of the European Master Program Plasma Physics and Applications. Besides research, it has in its role the continuous education and training. Since 2006, with the help of other colleagues of the university, including Kostas Petridis, we have run various Erasmus intensive training schools in plasma physics, lasers, optoelectronics, and nonlinear optics. And also, our aim is to help MSc and PhD students to fill up their programs. The starting point, as I said earlier, was a Marie Curie Excellence Grant entitled Development of an Innovative X-ray Source. That grant, the budget of that grant was about 1 million euros, and actually it got the success flag by the European Union, and that's why we got the title as an excellence, as a center of excellence. The aim, of course, as any research center in any university, is the education, the research, and the innovation, as well as the lifelong learning. This is a building, infrastructure. This area here is the area that the research is taking place. There is care about anti-vibrational granite-free environment in order to host the lasers, sensitive lasers, high-power lasers with short pulse. Usually, the anti-vibrational facilities for lasers, they use granite to isolate vibrations from 1 to 10 hertz, and above 10 hertz, the vibrations are being isolated by optical tables. This is the first lab that it is granite-free. It has a stable temperature, a stable humidity, and a slight overpressure, dust-free environment in the area where the lasers are installed. Also, I have to say that all the laboratories do not touch the building, the rest of the building where are the other facilities like offices and restaurants and libraries and etc. So, what research we are doing at the Institute? I don't like to separate the research in basic, technological, and applied. This is a mistake in my opinion, but for the purpose of this talk and to introduce you to the field, I will do this mistake, and I will say that we do basic research in understanding fundamental science phenomena related to laser, high-power laser matter interactions and plasmas. We develop new technology for the needs of this research, and this is what I will call technological research. And of course, we do applied research by creating products or services with direct social benefit. I will not have the time to discuss about this part today, but for example, here you can see a dynamic whole field imaging interferometry, which can be used, which is also the result of the research. Now it is an applied instrument that can be applied to many kinds of areas for social benefit. This is another example of technological research. This is a neutron source, which is developed at the Institute, and we use the neutrons for gamma ray spectroscopy. The key people of the institution, here you can see the permanent staff of the Hellenic Mediterranean University, people that are senior researchers that are paid by research grants, and also some of the collaborators abroad. And now we're in the process of accepting new scientists to become members of the Institute of Plasma Physics and Lasers. The equipment, the research equipment we have installed in the Institute has a value which exceeds actually the 10 million euros. The flagship of this equipment is a 45 terawatt, 25 femtosecond laser system, which can be focused at intensities which can exceed 10 to the 20 watts per square centimeter. We have two other laser systems of various pulse durations and wavelengths, from very short pulse durations, low energy, but this is a phase-locked, as we say, carrier envelope phase-stabilized laser system, which means that all the pulses have the same phase. We have other longer pulse laser systems, picosecond and nanosecond. We also have generators, X-pinch and Z-pinch, to generate plasma when a high current, fast current, fast rise time, high current passes through matter. And mainly we use X-pinch, Z-pinch, and plasma focus devices. I will speak to you about today about a Z-pinch device that we use for the research that I'm presenting today. We also have diagnostic devices for laser pulse characterization, dynamic whole field imaging interferometry for many applications that we do in the lab. This is a very interesting and necessary interferometric diagnostic. We are operating laser optical probing diagnostics for very fast analysis of the interior of matter, X-ray radiography, and gamma ray spectroscopy. So this is the area, the clean area where the laser is installed. This is a 45 terawatt laser system. The pulse passes through vacuum into a different area where we have the vacuum chamber that we perform the experiments. The beam of the laser, with the 45 terawatt laser, can be focused down to 3 microns focal spot size, giving intensities which can exceed the 10 to the 20 watts per square centimeter. Here you can see an image of the focus of the laser on a solid target. This is an X-pinch device. So here we have developed a device which can deliver high current of the order of 80 kiloamperes in wires. When these wires have an X geometry, they produce a point X-ray source, and here you can see the result of the resolution that you can have having a point X-ray source. This is a fly, and you can see the details of the X-ray radiography. This is a very important diagnostic, not only for biomedical research, but also for plasma research, since we are using these point X-rays to diagnose the interior of hot and dense matter. Of course, we do modeling in order to assist the experiments and the science we do. We have modeling capabilities. We have clusters, but now these days we are using the national GRNet cluster, the so-called ARIS. And of course, education, we are running the master course, Lasers, Plasma, and Applications. This is a course which started from the Curriculum Development Erasmus program. It was funded to be developed, and it was developed with the collaboration of other 7 European universities. Publications, here I have a summary of the publications of the members of the IPPL in various journals. I like this graph actually. 27% of the publications are published in journals with impact factor higher than 8, and the rest of the publications are published 50% between 2 and 8, and another 22% in journals with impact factor below 2. Some national and international awards. I will go fast into this. In August 2018, we had a highlighted research by Nature Communications, other awards in 2016, 2014, 2013, 2012, and of course, always we are grateful to Marie Curie Excellence Grants for giving us the opportunity to start our research and establish this institution. Our vision, here we are now, we have a front-end terawatt laser system, but slowly we would like to expand and have a petawatt amplifier in order to reach powers of the order of 200 terawatt, and maybe achieve later the petawatt range, and this will bring us having one of the most powerful lasers in Europe. Now, you understood maybe that we use energy to transform matter from a solid, from a gas, or from a liquid into the plasma state, and then we use the benefits of the plasma state for applications and basic research. For example, if you have a plasma, you can extract and accelerate electrons, you can accelerate protons. Depending on the target, you can have neutrons, and all these charged or neutral particles that can be produced from the plasma can be used for either basic physics research or important applications like accelerators and biomedical research. But in order to achieve these conditions, you need to fight with something which we call plasma instabilities. Plasma instabilities actually is a hot subject which is being investigated for many, many years. And of course, it will continue to be investigated in the future, since plasma instabilities are actually making us to feel uncomfortable when we want to use the plasma characteristics for applications, either in accelerating particles or in fusion research or in any kind of applications. You have the plasma instabilities that actually they play sometimes a not so good role. As I said, for the majority of applications, plasma instabilities are unwanted. We do not want to have plasma instabilities. For example, in fusion, plasma instabilities will make difficult to compress the plasma, but also in, let's say, accelerators, plasma instabilities will make difficult to accelerate the particles at very, very high energies. So we have to deal with plasma instabilities, not only from scientific curiosity, it is always a subject of nice physics, but also for the applications that they generate a problem. Now, you can generate plasma, as I said earlier, by passing a current through a target, by giving energy using a laser, or by very many other ways. When you pass energy into the other three states of matter, you heat matter, and then you change phase from the solid, the gas, or the liquid into the plasma. How do we study a plasma? There are two main ways to study a plasma. The first is to consider that the plasma is a fluid, and then use the fluid equations and the equation of state, as well as the continuity equations, in collaboration with the Maxwell equations, since we have charged particles, and try to understand the spatiotemporal dynamics of the plasma when this is excited from the other solid, from the other phases of matter. And we have two ways, two subways: either use the two fluid equations for electrons and positively charged particles, or combine these two in the so-called single fluid equations. But there is another way. There is a way using the kinetic models. This is the Vlasov-Maxwell system of equations. This is actually, in my opinion, an easier way to deal with the plasma, but you lose some of the nice physics which is hidden inside. For example, what do we use here? We use the Fokker-Planck equation, which is a statistical equation. We use distributions in the velocity space and the momentum space, and then we use the moments, the zero order moment, the first order moment, and the second order moment, to establish the mass conservation, the momentum conservation, and the energy conservation, which will lead us in equations to deal with the plasma expansion in time and in space. And of course, we have to use the Maxwell equations, since we have electromagnetic fields inside the plasma. This is a good way to deal with the plasma. As I said earlier, for most of the applications, when we have a dense plasma, we use the fluid models. When we have relatively lower densities, we can use the kinetic models. And then what do we do? To study plasma instabilities, we have to use the perturbation theory. So we have to perturb the plasma, one of the parameters of the plasma, or all the parameters of the plasma. So we have to do a perturbation to the main parameter, which is in equilibrium. And then the perturbation, for example, can be written as a planar harmonic wave. and then use the linearization method of the plasma equations in order to deliver and find out what is the dispersion relation of the perturbation. And from the dispersion relation, we can understand if the plasma will continue to be in an equilibrium condition after a while, or we will have an instability with a positive growth rate, which means that we will excite waves that they will continue to increase in amplitude. And we understand this from the dispersion relation. If we have a positive imaginary part of the frequency, omega, this indicates an exponentially growing wave, then we have an instability. If we have a negative imaginary part of the frequency, then this indicates that we have a damped wave, and this means that the perturbation that we have done in the plasma, it will be damped. So the key point is to find the dispersion relation. But until now, whatever was the way to study the plasma instabilities, either using the fluid models or the kinetic models, we had the problem that we should start from a plasma state. Not, we were forgetting the previous phases of matter. For example, when we had a solid and we were illuminating the solid with a laser to generate a plasma. To study the plasma instabilities, we should start all these models from the plasma state. In other words, we were considering that the other three phases of matter, the solid, the gas, or the liquid, did not play an important role to the exploitation of plasma instabilities. Here, for example, you can see some kind of plasma instabilities. This is the Rayleigh-Taylor instability. It's exactly the same with a fluid Rayleigh-Taylor instability. In plasmas, we call it magnet or Rayleigh-Taylor instability, since we have the magnetic field. And you can see here, if you have a uniform plasma, as it expands in time, you can see all these disturbances in space that we call it magnet or Rayleigh-Taylor instability, and this is the growth rate. I will not go into details in these kind of things. We have the kinetic instabilities, which are generated if we perturb the Maxwellian distribution of in the momentum space of the particles, and this the plasma tries to be reordered, and this plasma effort leads to the generation of the so-called kinetic instabilities. We have the streaming instabilities, which are related to the different charges of particles that can exist in a plasma. So when, for example, we have electrons, imagine a plasma with only electrons and protons. The different species have different drifts. Therefore, they have drifts relative to one another, and this fact leads to the generation of waves which are excited, and they gain energy from the drift energy of the charged species. As I said earlier, until now, we should examine plasma instabilities starting from the plasma state. So this is a solid target. Imagine that we add energy, for example, using light, using particles to hit the target. When we wanted to study plasma instabilities, we were forgetting the previous state, and we were starting from the plasma, high density material with no elastomechanical properties. But this was actually a problem, since as we predicted, the phases which are the phases before plasma generation actually play an important role to the generation of plasma instabilities. Actually, they offer the seed mechanisms to generate plasma instabilities. When we have a solid, we know that we have the thermoelastic regime, then we go into the plastic regime, and then we have the fracture of the material if we continue to give energy and break the lattice. So this is what we wanted to study. We wanted to study the effect of the phases before the plasma into the seeding mechanism of generation of plasma instabilities. The easiest way to do that is to use a wire, a metallic wire, copper. Imagine a copper with a diameter of the order of 300 microns that is being positioned between an anode and a cathode, and the fast rising current heats the material. Why we choose this geometry? Because this is a very, very well-studied geometry in the plasma phase. We know exactly what are the instabilities that are generated there. And this is the reason we started from this geometry, and we did not start from another geometry, let's say from a laser matter, laser solid target interaction. So the Z-pin geometry, as I said, is a convenient geometry because we know exactly what are the modes of the instabilities that are generated. I will show you real pictures later. So these are simulations about 15 years ago that they show that this solid wire, when heated by a high current and expands in time, you can see that it's not uniform at all. You have instabilities. This is the m equals 0 mode of the instability. And here you can see a mixture of the eigenvalues, m equals 0 and m equals 1 eigenvalue of the instability. That's why you can see that you also have something like elliptical movement of the plasma over here. So there is a need to investigate the plasma instabilities starting from the beginning of the process. In other words, starting from the solid material. The reason this was not an action, a research action in the previous years, is that this is very, very demanding. It has multi-physics that you have to consider. And more importantly, you have to consider the phase change problem between the solid, the liquid, the vapor, and the plasma. Because when we heat a solid material, we start from the thermoelastic phase of the material, but as the temperature increases, then we are passing into the melting phase where we have a liquid, and then we are moved into the vapor phase, and finally the vapor is ionized and we have the plasma phase. So we need to solve, and we need equation of states for the phase change between the different phases of matter. And as you know, this is one of the most difficult problems on this planet, and the phase change problem always will be something that has a great difficulty. Also, we had to continuously and simultaneously consider effects like electromagnetic, thermal, elastoplastic, and magnetohydrodynamic when we are in the plasma phase. On the other hand, the experiments are very difficult because if you want to set up experiments and diagnostics to diagnose the phase change of the matter, this is also something very difficult. The traditional diagnostics, they can diagnose, let's say the plasma phase, they can diagnose the solid phase, but it's very difficult to diagnose the phase change. So we should also develop for this kind of research a new diagnostic, which is based on the Fraunhofer diffraction of light, of a laser, in order to be able to characterize the material from the solid until the end of the melting phase. So why we choose a thick wire? We choose the thick wire because when you pass current from a thick wire, you have the so-called skin effect mode. The current flows through the skin, and this gives us the opportunity to have all phases of matter simultaneously in the wire. So we have plasma, we have a solid in the middle. All phases of matter are present at the same time when we use a thick wire. And this is the reason actually that we use the 300 microns diameter copper wires. Here you can see the design. This is the machine which is developed with the help of the people of the Department of Electronic Engineering that are now specialists in developing such high current, fast rise time optoelectronic devices. This is the so-called X-pinch device. Here you can see the anode, the cathode. Here you can see the load, which is an X, two copper wires touching in the middle. This is for the biomedical applications using the point X-ray source that I showed you at the introduction. But for the purpose of this talk, imagine that here you have just a single wire touching the anode and the cathode of the design. And here you can see the rise time of the current, which is of the order of 60 nanoseconds, 10 to 90% peak. So in order to diagnose the spatiotemporal dynamics of matter and diagnose all phase changes, we used the laser, which was synchronized with the Z-pinch device. And we used the laser in order to be able to capture very fast images of matter. The rise time and the time duration of the plasma expansion in space in the vacuum is of the order of a few tenths of nanoseconds. The laser was of the order of 100 picoseconds. Therefore, within 1 nanosecond, we could have 10 frames. So we have a very, very high time resolution in diagnosing the phase change of matter from solid until the plasma phase. So for the thermoelastic regime, where the solid keeps its elastic properties, we used a Fraunhofer diffraction, a modified Fraunhofer diffraction diagnostic to measure the expansion of the wire. We needed here to have a resolution, a special resolution of the order of 1 micron in order to be able to see the expansion changes while the material was heated. We could use the Fraunhofer diffraction also for the melting phase. And then for the vapor phase and the plasma phase, we used Schliering imaging, interferometry, and shadowgraphy. So this is a laser, this is the Z-pinch, and then we have the channels, interferometry channel, the shadowgraphy channel, and the Schliering channel to diagnose matter. Now, for the simulations now, in order to simulate the target's response in time, we should use, of course, a strength material model, and we use the very well-known Johnson-Cook model, along with the equation of state. And one of the reasons actually that we used copper is that copper has a very, very well-defined equation of state for all phases. And this equation of state is also tabular, which means that it has been also proved by experimental analysis. So without an equation of state, it is impossible to do such kind of research because it is impossible to diagnose the phase change between the different phases of matter. We took into account the temperature-dependent properties of the thermal expansion. We took into account the changes in the thermal conductivity of the material. We took into account the specific heat, as well as the latent heat of the melted copper when we had the melted phase. But we also had to consider the electrical equation of state. So we should find an equation to identify the electrical conductivity versus temperature. And we used for this purpose the Burgess model, because the Burgess equation of state is actually the most reliable because it is experimentally validated. So the equation of state is indeed required in order to simulate the behavior of the material. Now, we used the Grunetian equation of state, which is actually the most commonly used equation of state for metals. And for copper, actually, the Grunetian equation of state is very, very accurate. And because the material is also because it also considers the high energy deposition and the impact of the deformation for the high strain rate of the material. So we should use actually a multi-phase EOS. And this multi-phase EOS should be used not for the entire material, but we should divide the material into regions. Actually, we divide it into 3 regions, region 1, region 2, and region 3. And we should use a different equation of state for each of the regions of the material. For the solid phase, we use the Grunesian, as I said earlier. For region 2 and 3, where we have other phases of matter, we use the CSAM multi-phase equation of state. And actually, this combination, we found out that it gave us the most accurate results in comparison with the experiments. I will not go into further details about the equation of state. The modeling, actually, we used the FEM modeling with the help of the simulation team of the IPPL, which is led by the colleague Vasilis Dimitriou, and the other colleagues that they do simulations here at IPPL. The finite element method and all the multi-physics simulation should consider, as I said earlier, the phase changes. So we should use the finite element method, but also the magnetohydrodynamic codes in order to capture the phase change between the gas and the plasma. And for the mathematical modeling, in the thermoelastoplastic regime, we use the Cauchy momentum equation, the mass conservation, the energy equation, and the thermal equation. We, of course, in correlation to the Maxwell equations. The strength material model that we used, as I said, was the Johnson-Cook flow stress material model. We had the equation of state, but also the equation of state for the electrical resistivity. I will not go into details about the Berger's electrical resistivity model. I will continue and I will show you now the results. Let's start from the thermoelastic regime. This is the regime where the solid material retains its thermoelastic properties. This is the result from the Fraunhofer diffraction diagnostic, where we can identify the expansion of the heated wire in space. And from the comparison of the target before the heating and after the heating, we can identify what was the expansion of the radius of the wire. For example, here you can see that at the end of the thermoelastic phase, we had an expansion of the order of 7 microns. From this, you can understand that we needed a spatial resolution of the order of 1 micron in order to be able to resolve this matter. And actually, it was very difficult to find out a diagnostic. And indeed, this modified Fraunhofer diffraction laser optical probing diagnostic gave us the solution and gave us the opportunity to measure such expansions of the order of the micron. So here you can see the expansion of the wire. This is the radius of the wire. So this is the simulation, the black squares, and the white are the experiments. And you can see the very, very nice correlation between and agreement between the experiment and the simulation. So this is now 2 images in the plasma phase regime. You can see the wire. You can see the plasma instabilities. So these are the plasma instabilities. The black region is the region where the density is either solid or the plasma density is very high, and the laser which captures this image cannot propagate through. but you can see the instabilities. Actually, this is the magneto-Taylor instability, and you can see the comparison between the experiment and the simulation. This is at a later time where the plasma has expanded more. You can see the experiment and the simulation, a very, very good, actually, agreement. The wavelength at this time is of the order of 270 microns, and the simulation gives 255 microns, an excellent agreement. Here you can see an expanded version of the previous, the instability, the experiment, and you can see the simulation. And the video will be better, actually. So this is the wire, which is heated by a high current and expands in time. And you can see the instabilities that are generated on the surface. Actually, you can see also that we do not have one single wavelength, but we have more than one wavelength. You can see the expansion of the plasma now in space. And here is when a clear M=0 mode of the instability has been generated. So this is actually, there is an excellent agreement between the experiment and the theory, the simulation, which gave us the opportunity to establish that in order to predict what are the instabilities that are developed in the plasma phase, we must start and take into consideration the solid phase of matter, because the perturbations that are generated, the elastoplastic perturbations that are generated in the thermoelastoplastic phase of the material is actually the seed for the instabilities that are generated later in the plasma phase. And to give you an example, when we were studying plasma instabilities, when we were doing simulations for plasma instabilities, when we wanted to perturb the plasma, we were taking sinusoidal perturbation, multi-wavelength perturbation. So we were a random perturbation, and we were trying to establish which is the better perturbation in order to match the experimental results. Now we solved this. We do not need to perturb the plasma by an artificial function. We need to take the thermoelastoplastic regime of the material, find out the perturbations that are generated there when you heat matter, and then use these perturbations, which are the real perturbations that they seed the plasma instabilities later when matter has passed into the plasma phase. Now, this result was actually very important because it could give us the correct answer how
Michael, sorry, you have 5 more minutes.
phases of matter can influence and the generation of plasma instabilities. So the next step was to explain some unexplained results for elliptical structures that were being observed in high current solid target experiments, wire experiments that they were being used for in the mag-life concept. The mag-life concept is to compress matter using high magnetic field. And there, people observed that there are helical structures in the plasma that cannot be explained from the present theory. So what we did, we continued the research, and we found out that within the thermoelastoplastic regime of the interaction, we found out that a non-linear magnetic diffusion wave is generated. Actually, this was observed also by by other groups. And here you can see, for example, the growth rate of the instability in the thermoelastic regime. I forgot to say that we gave a name to that instability that I discussed you until the previous slide. And we gave the name electrothermomechanical instability, since it involves the thermomechanical characteristics of the material. And here you can see that the simulation shows a shock wave which is generated. So as time progresses, the growth rate of this electrothermomechanical instability, it has this shape here. And we wanted to explain why this shape is present in opposition to the analytical model. But of course, you see that the growth rate increases, but it doesn't have this strange shape, I would say. So this is now the current density distribution. These are simulations at various times. So here you can see the current density as a function of the radius of the wire. So we have the wire and we have the current density, let's say at different depths inside the wire. And here you can see pressure. So we can see that we have a radial, actually shock wave, which is generated inside the material. And why this radial shock wave is generated? It's generated because we have a non-linear magnetic diffusion wave. So the magnetic field, which is generated by the current which hits the wire, is above a certain value, and we reach the so-called non-linear magnetic diffusion regime, where the resistivity increases or the conductivity decreases rapidly and generates this shape of the current density distribution. So another important observation here is that if we plot the time dependence of the perturbation growth rate and we isolate the longitudinal and the azimuthal growth rate of the instability, we see that at the end of the thermoelastoplastic regime, there is a difference. And this is there is about 25%, 23% difference in the growth rate, in the instability amplitude between the longitudinal mode of the instability in relation to the azimuthal mode. But on the other hand, this longitudinal and azimuthal wave number.
Michalis?
Yes, Kostas.
You have not more than
I know I have 10 minutes yet.
Okay, thank you.
Yes, I will finish in 5 minutes. So we can see that the longitudinal and the azimuthal wave number of the instability, although they start having a different difference, as time progresses, they converge. And at the end of the thermoelastoplastic phase, they have almost the same value. And the question now is, this difference in the longitudinal and azimuthal wave number, can this be the reason for the elliptical structures that are seen in these experiments when high currents passes through wire materials? Here are experimental results showing shadography, slitting, and interferometry. You can see, and this is in the plasma phase. We can see that in the plasma phase, and we can resolve this into these images, we have not only one wavelength of the generated instability. For example, here you can see clearly 1, 2, certainly. And maybe we have more wavelengths. And the question is, we have a preferable mode, which can be 1 or 2, later in the plasma phase, and how these preferable modes are influenced by the fact that in the thermoelastic phase, the longitudinal wave number is different in comparison to the azimuthal. This will, of course, remain an open question, but we believe that this fact may explain the elliptical structures, the unexplained elliptical instability structures that are observed in the magnetic liner experiments. And here you can see the whole picture of the material, the instability amplitude of the inside the material from the thermoelastic regime down to the plasma phase regime. And you can see the phase changes. For example, this is a point where we change phase, and we diagnose this with experiment. And you can see that when the material changes phase from gas into plasma, you have a rapid increase of the instability amplitude. The green dots here are experimental data, and you see how well they match the simulation. Unfortunately, we have experimental data only for the longitudinal amplitude of the instability, because as you understand, to measure the azimuthal amplitude, so to have experimental data on this blue line, you need to have X-ray radiography, hard X-ray radiography, in order to diagnose the material inside in a very dense core. But this is enough for us actually, and you can see here a zoom view how well is the correlation between theory and experiment. So to conclude, we have actually found out that the thermoelastic phase of a heated material can be the seed for the instabilities which are present later in the plasma phase. We have named this instability as the electrothermomechanical instability. The electrothermomechanical instability is a very, very possible candidate to see the magneto-Rayleigh-Taylor instability that is present later in the plasma phase. The study demonstrates that this anisotropic growth rate between the longitudinal and the azimuthal wave number of the instability can be the answer for the elliptical structures, instability structures that are observed in the plasma phase in magnetic liner inertial fusion experiments. And we can say here that this electrothermomechanical instability, the anisotropic growth of the two modes, of the longitudinal and the azimuthal wave number, is actually an observation which can indeed answer these questions, and that's why we believe that we need to continue this research and acknowledge the HELAS CH program, which is actually a project which is funded by ESPA and the Hellenic state to generate national research facilities. One of these national research facilities is also the Institute of Plasma Physics and Lasers within the HELAS CH research facility. And we would like to thank and acknowledge funding from this project for the research that I have already presented to you. And actually, thank you for your attention. And if you have questions, I'm happy to answer.
Thank you very much, Michalis, for this nice talk. Please stop sharing the screen in order to be able to continue with the Q&A session. Please, whoever has a question, to raise his hand or switch on his microphone and ask Michalis directly. In the middle time, so I have some questions, Michalis, to ask, and I'm sorry if my questions will be naive because I'm not in the field. First of all, I will start from the beginning of your lecture, and I would like to ask you, since you are building devices that they generate X-rays, what is the main applications that you envision? And I would like to ask something about the repetition rate of your X-ray sources.
All right. The X-ray source that I presented to you earlier, this point X-ray source, and let me share the screen again. So this device here is a single shot device. So we load the target and we have a single shot. We get the X-ray radiogram and then we have to load the target again. So this takes time. This is for the very hard X-rays. For lower energy X-rays in the XUV range, we have developed another device which operates at 1 Hertz. This is called the plasma focus device, where you can use this device for high repetition rate experiments. But of course, if you want to have very high energy X-rays, and this is an X-ray radiogram using 10 kV X-rays, then you need to use a solid. And of course, since you have to use a solid, you have to load, shoot, take the X-ray radiogram, and then load again, have another shot. So you cannot shoot in a high repetition rate because you have to change the target. Not because the machine cannot operate at a higher repetition rate, but because you have to load the chamber since the load is a solid target. If the load is a gas, of course, it can operate at 1 Hertz, and we have developed another device which we call plasma focus for XUV X-rays and also neutron production for soft X-ray radiography as well as neutron gamma ray spectroscopy.
And what was regarding this picture? What is the exposure time?
This is just one single shot. It's 60 nanoseconds.
60 nanoseconds. Okay. I'm asking this because
60 nanoseconds is 60 nanoseconds is the rise time of the current. Okay, the plasma. It's let's say this is a single shot, so it's let's say a few hundreds of nanoseconds. It's if you consider that the rise time of the current is 60 nanoseconds, so you have the pinching at around, let's say, that time, the plasma persists there for a few hundreds of nanoseconds. So this is an X-ray radiogram from the X-rays produced by the point source in the vacuum. It's very short. It's very short.
Could I ask some questions?
Of course, John. Yeah, Michalis, please stop sharing the screen in order to be able to check the attendees. Okay, so the floor is, just a moment. Hi, Alibek.
Are you okay?
Yeah, I'm okay, but
hello.
Just a moment. Just a moment, sir. So, Georgios Kapoulakis, the floor is yours.
First of all, very nice stuff, Michalis. I really enjoyed what you said. Let me ask you, first of all, is it possible experimentally, that was not clear to me, to see inside the wire? If you cut it, can you see through what is going on through the wire? Experimentally.
If you cut the wire after the shot?
No, I mean, while you perform this experiment, is it possible without touching the wire to see what is going on inside the wire?
To see what is happening inside the wire, you need to have very, very hard X-ray spectroscopy. That's why we have developed actually this X-ray source, 10 kV. And now we are in the process of doing a simultaneous experiment, having the X pinch in the vacuum chamber in order to take an X-ray radiogram in the wire. Until now, we could not diagnose inside the wire. That's why we could not have the azimuthal component of the instability, and we had only the longitudinal, because for the longitudinal on the surface of the wire, we used the laser to have shadography, steering, and interferometry to diagnose it, but we diagnosed the surface of the wire. If we want to diagnose inside the wire, we need to use hard X-rays, and this is the reason one of the reasons that we have developed and we have tested this machine, but we have not yet have images from inside the wire.
And when you use these X-rays, would you destroy the wire?
No, the X-rays will not destroy the wire.
Okay. Also, another question, do you have any fitting parameters in the modeling that you do? Is this a parameter-free model, or do you have fitting parameters?
No, we do not have any fitting parameter because we take the real equation of state of the material. We use the Burgess model for the conductivity of material. And actually, we use the tabular Burgess model so that this is experimentally validated. And this is actually why we did this research, because we did not want by hand to put the parameters into the model. We took the real intrinsic thermoelastomechanical parameters of the solid material, and we used the real equation of state of the material and the conductivity equation of state, the real numbers, and we left the model alone to give the result. Actually, this exactly was the problem for the last many years. That when we had a simulation, we should put the perturbation by hand, either a sinusoidal, a multicolor sinusoidal perturbation, or a random perturbation, and then we were playing with the perturbation in order to match the experimental results. But now this is not happening. Now we take the real parameters of the material, and these real parameters are introduced into the simulation to give us the results. And we have seen that exactly this is the result that the model produces fits excellent the experiment.
That's very nice. And a final question, which was not clear.
While previously we had to play, to change the perturbation, to change the amplitude of the perturbation, to change the wavelength of the perturbation in order to see if the experimental results are matched. This is the innovation we have done.
Indeed, because you can, yeah, of course. A final question. I understand you have these phase transitions between the various phases that you mentioned. In the modeling, how does this become possible? I mean, you have you use a Boltzmann equation for the various phases and you couple them. I mean, it's not clear to me how you handle this problem.
Yes, we always use the most reliable equation of state so the question is, how do we decide when we change the equation of state from the Burgess to the CSAM equation of state, for example?
Yes.
This is done, and the criterion we use for this is the temperature. So we use the temperature criterion, and when for example, we see that this cell of the simulation has this temperature, then from this temperature, we change the equation of state, and we pass into the next most reliable equation of state for this window of parameters of temperature.
Okay, thanks a lot, Michalis.
Thank you, George. And I think that Muslim Zaripov has a question. I don't know if I cannot pronounce the name very well. Mr. Zaripov, if you are with us, please switch on your camera or your microphone and ask the presenter your question. But anyhow, Michalis, at the end of your presentation, you saw these instabilities and you are wondering if you have one wavelength or multiple wavelengths as a result of the instability. Did I understand well?
So, yes, actually, I said that always when the material reaches the plasma phase, within the plasma phase, there is a preferable mode of the instability. For example, if you have a wire, usually the preferable mode is the M equals 0 instability. The M equals 0 instability is one frequency, is the main and the preferable frequency of the instability.
So
you may also have another mode, the M equal 1 mode, or you may have a mixture of modes. And we have also seen this experimentally, a mixture of modes that they give you, let's say, elliptical structures in the plasma phase. But always there is a preferable mode. So the question is how the plasma decides which is the preferable mode of the instability that it will be developed inside. So and the question is further, has the thermoelastoplastic phase of the interaction an effect? Which mode will be the preferable mode when the material reaches the plasma phase? So this is the critical question.
And Michalis, I would like to ask you, I mean, this is something that experimentally or the simulations reveal?
Both experimentally and with simulations.
Experimentally, what did you use? Did you use a coherence experiment? So by a coherence experiment, you defined that you have such a language, such a spectral purity of the emitted electromagnetic wave. How did you measure it?
Experimentally, in the plasma phase, we see in the instability using optical probing diagnostics. For example, here you can zero instability.
A coherence experiment. So you try to do a coherence experiment in order to define how many modes do you have?
Yes, we use interferometry, shearing, and shadography.
Okay.
And from these diagnostics, we see the modes of the instability and the wavelengths of the instability.
Yes. This is clear now.
So we always see that in the plasma phase there is a preferable mode. But why is this mode?
Yes.
This is not understood. And sometimes we see in the plasma phase helical structures that are generated. And actually in the mag-life.
Did you try to check the dimensions of the wire or the dimensions of your experimental apparatus? Because you mentioned that you're observing longitudinal modes, and the longitudinal modes mainly is like a standing wave. I mean, this is...
We observe longitudinal modes and azimuthal modes. Mm-hmm. So we have both azimuthal and longitudinal. For example, if I do a share screen again, you can see here the growth rate within the thermoelastoplastic phase of the interaction. You see this is the longitudinal wave number, and this is the azimuthal wave number of the instability, where initially they have a, let's say, 20-25% difference, and then they converge. And the question is, if I put an external magnetic field, now this is the research we are doing now to explain the helical structures that are being observed in mag-life at the States, at the United States. If we put an external axial magnetic field along the axis of the wire, will this difference in the kz and k theta will lead into a helica? Yes, it will lead. This is what we are doing now. I have not presented this yet because we want to be 100% sure, but yes, this difference in the wave number between the azimuthal and the longitudinal most probably can lead to a helica. And this is the helica structures that we observe when an external magnetic field is applied along the axis of the wire.
Mm-hmm. So, and finally, Michalis, I like very much that you are studying these instabilities because from what did I understand, this is like a problem regarding your final product, like the production of neutrons or the production of X-rays, whatever you are producing through these devices. So you would like to study the problem. And so I suspect that you have some ideas how, since you are studying these instabilities, what are the future plans? How are you going to control the instabilities after the second stage of your research?
All right. This is the most crucial question. The instabilities is a disaster because we do not want the instabilities for any application, any plasma application, especially in fusion, for example. The instability is a disaster. You cannot avoid the instabilities. It's impossible to avoid the plasma, not only the plasma, the solid phase, the melted phase, the gas phase will develop instabilities. The nature likes to develop instabilities. So you cannot avoid them. You must find the reason that this instability is developed. So you must find the seed mechanisms of the instabilities, and the seed mechanisms we have found that are in the thermoelastic phase thermoelastoplastic phase of the interaction. So what you can do, you must end your application before the growth rate of the instability destroys it. So you must use the plasma, and you must find plasma geometries where you stop your application. For example, if you want to have an accelerator, electron accelerator, so you have to accelerate electrons. You must stop the acceleration when the growth rate of the instability is still low.
And what is the impact? And what is this? What is the impact to the final result, to the output?
For us,
Yes.
for us is huge. It's huge. For us, it's huge. For example, now we're trying to develop the applications and impose these new findings when to stop the application, when to stop, for example, because this is valid for many applications. It's valid for the compression of matter, is valid for acceleration of particles. So you must always do an experiment and stop the application before the growth rate of the instability is high.
Mm-hmm. Okay, thank you, Michalis. I think that we should stop here. If there are no more questions, so I can see that this is the case. Michalis, thank you very much for your contribution in this nice talk. And I would like to thank also all the participants from my point of view, and also from George Kavoulakis for your participation. So I hope that I will see you again next Friday. Excuse me? I'm sorry, I'm sorry for the participant. We cannot. We have some technical issues in order to listen him. So thank you very much. Thank you.
Minute.
Yes, Alibek, please.
Dear Costas, I am the writing at the meeting in Karshi Engineering Economics Institute Hydrotechnical Engineering Department, and five staff visiting our meeting, and head of Hydrotechnical Engineering and Mr. Sabir Yeshef and visiting our meeting, all the colleagues, the department, all the thank you very much, and the meetings.
Thank you very much, and
all the visiting in from Uzbekistan in professors, Grecian professors.
Thank you very much, Alibek, and we hope to have you also in one of our future talks every Friday at 10 o'clock CET. Thank you, Michalis, again. Thank you, the participants, and see you next Friday. Next Friday at 11 o'clock Greek time, 10 o'clock CET. It is a great pleasure to have among us Professor Aristidis Kyprakis from the University of Edinburgh. Actually, Aristidis was coming as a graduate student of the ex-Technological Education Institute of Crete. He moved to Edinburgh, one of the most historic universities in Europe, and he thrived. His career since this moment was an excellent, based on the knowledge that he has received from our university. So I hope that I will see you next Friday at 10 o'clock CET, 11 o'clock Greek time with the talk from Professor Kyprakis. So thank you very much, and have a nice day, and be safe. Thank you, Michalis.
1 minute. 1 minute.
Okay.
Hello, everybody.
Hello.
I have got one question to Michael, Mrs. Michael.
Okay, Mr.
Mr. Michael, yeah. Please talk about some information master classes. How qualification will be as for study such education master classes? You talk about it. You talked about it.
Yes. The qualification is a bachelor degree in engineering or physics or mathematics, maybe chemistry, and from engineering the preferable bachelor degrees are electronic, electrologic engineering, mechanical engineering. These are the preferable. Or also chemical chemical engineering, mathematics, physics.
Thank you for your answer.
Thank you for the question. The Hellenic Mediterranean University is always welcome any student that he would like to follow one of his postgraduate degrees, and we hope very soon to be able to accept also undergraduate students within our facilities. So thank you, be safe, and see you next Friday. Bye-bye.
Thank you very much, Kostas. Thank you everybody.
Thank you,
Bye.
Mike.